Okay, without any further delay, I would like to invite Mr. Tosh Rayadhurgam from Meta to please join us in the stage. Please welcome Mr. Tosh, to the stage.
Okay. Hey everyone, am I audible? All right. I see a few people returning from lunch, so let's get started. So yeah, today I'm going to be talking about searching with LLMs. I'm Tosh. I work in Meta. I think over the span of the past decade, I've been involved in a lot of recommendation systems uh, at Meta and also at Amazon, and a small startup called Lyft in San Francisco. So today I'm going to be talking about something I've been working for a while. The interesting thing about search is it's one of those problems that kind of looks like it is solved until you actually look at the data, right? So we have these systems that serve billions of queries, but when you dig in, you basically find that 80% of these unique queries that people type, right? We essentially have no training signal, right? So these models are basically guessing. And LLMs basically change these equations in interesting ways. This brings a massive prior from pre-training that kind of lets you handle queries. So I'll share some techniques that worked, some of which were actually surprising, and some that didn't work, which is more useful, I would say. And how we kind of ended up with a 20+% improvement in NDCG, which translate to a good amount of business impact. So let's go to the next slide. All right, there you go. Yeah, so basically, the three components. All right, let's see. Okay, so I'll be talking first about query, and then about content, and then how we're using LLMs as judges. So first thing about query, you can see that I made a query on my Amazon for a Suits sofa, and I get weird things, right, related to the sofa, but is this what I'm searching for, right? So this is what we're going to basically talk about today. So in essence, what we want to, let's see. Okay, all right. So what we're looking at right now is this whole traditional approach with past clicks, right? So what's going on with traditional approach? Yeah, go ahead. Is that better? All right, okay. So yeah, what's going on with traditional approach is, you have a query for Suit Sofa, and then we look at past clicks, and then we see, okay, what gets the conversions of clicks there. However, as you saw in my previous slide, we're getting things unrelated to the sofa, right? We were getting things like the cleaner. Let's go back to this one. I guess there's some issues with this. Okay. So we're getting some Suit Sofa cleaner, we're getting some covers and brushes, but this is not what we are looking for, right? So any guesses as to what's going on here? Right. And any idea what our search systems are doing? Yeah. So this is the traditional approach, right? It only works well, as he pointed out, when you have data, right? The idea is simple. We observe what user clicks when they search, Suit Sofa, and we aggregate like over thousands of sessions, and you basically learn that 85% of the clicks basically land in couches category. And now you have to look up a table, which is, hey, how do I query this category distribution? And then, that's essentially what you're doing is you're learning the probability of a category given a query, right, from the empirical click distribution. So now the problem is the tail. And in search, basically tail is massive. So what do I mean by that is, what do we do when we've never seen this query before? Or what happens when we've seen it twice, which is still statistically meaningless, right? And that's where a traditional approach basically breaks down. And that's where we found LLMs actually provide most value. So let me kind of go through the next slide, where what we're doing right now. So in this slide, it's a basic picture. A user is typing suit sofa, and the question is, what do they actually want, right? What we're doing here is using LLM as a semantic parser. So that means query comes in, and LLM extracts your structured features. And in this case, category is basically living room or couches. And the material is suit. And then we use those structured features to query the search index, right? Sounds simple. Now, what this buys us is, if you think about search engines like Google, or even in this case, Amazon, right? The search engine can now filter by category. And that boosts the material match. And the user gets sofas and not cleaners, in essence. Now, the obvious question was, couldn't we learn this mapping from click data, right? And we saw, what happened to that in the previous slide, right? Now, moving on, I want to kind of discuss what does the LLM enhanced pipeline looks like, right? So let me give you a framework for thinking about this systematically. There are 4 places in a LLM pipeline where LLMs can actually intervene. And they all have different characteristics. The first is query understanding, right? What we're doing here, this is online, like at query time. And what you're doing is you're extracting structured representation from raw query, right? And the constraint that you have here is latency, because it's an online experience, right? So you maybe have got 50 to 100 milliseconds latency before you start hurting user experience, right? And then the second is content understanding, right? Now this is offline. You do some batch processing. You're trying to enrich your document corpus with like any attributes that you want to extract, right? And this is often the best place to start using LLMs, because you pay the LLM cost once per document, right? And this is amortized across all the future queries. So you have 0 runtime cost here, right? And the third one is similarity and ranking, right? So this is where what you're doing is you're combining signals, and then you have your BM25 that scores, and then we have embedding similarities. And the LLM contribution here is indirect, right? It's basically providing features that ranking function consumes. And finally, LLM as a judge, right? So this is your evaluation loop. So can we replace expensive human labelers with LLM judgments? The answer still is partially, I would say, with caveats that we're going to discuss. I think the key insight is that these have different computational constraints. And what I mean by that is content enrichment is almost always worth it. Query-style LLM calls really need careful cost management. So we're not going to talk about industry applications of cost, rather in this talk. I want to discuss the next part in query, which is query understanding, right? So let's kind of be precise about distribution here, right? So because this is really the crux of why LLMs matter. We've computed, query frequencies over, say, 90-day traffic. And then you have your head queries, which is your top 5% by unique query count. These represent about, say, 50% of total traffic, let's say. And these are your, in the example, couch or say, iPhone or Nike shoes or something of that sort, right? And traditional ML really works great here. And because you have rich click signals, we have stable patterns. So LLM need is not really enticing in this case, right? And then you have the torso queries, right? What's happening here? These are like about next 50%, and they kind of represent maybe 30% of the traffic, right? So say, things like, I need blue running shoes of size 10, right? You have some signal, but it's noisy, and the models are uncertain here. And then you finally have the tail, which is 80% of all your unique queries, right? But they represent only 20% of the traffic. Now, here's the thing. These queries are literally some queries that you've never seen before. Or you may have seen once, right? There's this whole, say something like mid-century teak credenza, or something of that sort, with maybe brass hardware. Like, how often do you see such queries, right? So these are tail queries. Now, for these queries, for the tail queries, traditional machine learning has nothing to work with. You can't learn the probability of category given, query when you have a probability of query is 0 in your training series, right? This is where your LLMs shine, because they generalize from pre-training to queries that have never appeared before in your data. And there's a compound problem here, right? That is the cold start trifecta. Now, anyone who's worked on, say, production ML knows that cold start is a very big issue, right? You have new queries, you have new products, and you have new categories coming along, right? And each product launch has no click history at all, right? Now, it could be like an emerging category where there's no training examples, right? And LLMs potentially address this, even though the mechanisms may be different. I would say the bottom line in this case is, if you're only optimizing for head queries, you're kind of leaving 80% of your query vocabulary on the table. With that, I want to jump into zero-shot query classification, right? So let's kind of look at the actual implementation here, right? This is like standard zero-shot classification. You're prompting the LLM with a query, and what you're getting is a list of categories that are valid. You ask it to clarify, right? The prompt is pretty straightforward in the left, right? System is kind of like establishing the task, and then you pass the query, and then there's a list of valid categories, and then you end up asking for the most appropriate one. Nothing fancy here, right? But there's a detail that turned out to matter, right? We basically include an explicit escape hatch here, which is return no classification fits if it is ambiguous. I'll explain why in a moment. Let me walk you through these results here, right? BM25 baseline kind of gives us 0.54 NDCG. Now, if you add a basic classifier, right, that's about 50% classification accuracy. Now, that bumps it to 0.561. So you have about a 3.7 or to 4% improvement just from prompting. So still, no training data, no fine-tuning, right? Now, with the unknown option, the accuracy actually goes up to 55%. So still, you get about 66% accuracy, and you have perfect classification, right? Now, a few things kind of jump out here, right? First thing is there's a ceiling of 0.575, right? Even that perfect classification only gets you so far. Now, category is actually a useful signal, but it's not a dominant one. And the second thing is the relationship between accuracy and NDCG is kind of sublinear, I would say, because you're going from 50 to 66% accuracy, that barely is moving your NDCG. Now, this kind of tells us the type of error matters, right? Not all the misqualifications are equal. And third, I would say this is a key insight, is the unknown option is doing some interesting work there. And we're going to discuss that next. So I would call this I don't know strategy, right? So it's a very simple, but it's an important idea. The logic is, if the clarification is going to help, let's use it. If not, let's skip it. Now, it's simple. Why does this matter, right? Because in retrieval, when you have a wrong classification, right, that actively hurts, it's not like standard classification where wrong and abstain are similarly bad. So if someone searches, say, maybe a vintage lamp, right, you incorrectly boost outdoor furniture, right? You push the relevant results for down and then some irrelevant results up, right? That's worse than doing nothing. So what we do is we implement something called selective prediction. The classifier basically outputs a category, either a category or just I don't know, right? When it abstains, we fall back to the base retrieval, which is BM25. And you also add some embedding similarity as well. We're not doing any category boost yet, right? Now, empirically, this actually improves robustness. The system is degrading gracefully on hard queries rather than kind of confidently getting them wrong, which is what we've all experienced with LLMs in the general world, like hallucination, right? Now, that brings us to the next one, which is hallucinated classifier, right? So I know the font is kind of small. Let me just explain. So this is probably my favorite technique in the whole pipeline because it's counterintuitive and it works well. The problem is, let's say our taxonomy has about 1,200 leaf categories, right? Now, to represent that in a prompt, you need roughly about 6,000 tokens, right? And now at scale, say you have millions of queries per day, that token cost adds up fast, and you're paying for it on every query, right? Now, your standard solutions are like you're doing some decoding in a constrained way, or you're doing RAG or retrieval augmented classification, right? And then you classify that over that subset, right? Both of them are going to add complexity. Now, this approach is very simpler, but it's a bit weird. So we actually let the LLMs hallucinate. And instead of giving the LLM our taxonomy and just asking it to pick, we just ask, hey, what category is this? No constraints, right? And the LLM generates whatever category string it wants. And we might say office or, I don't know, executive chairs for a query about desk chairs, right? Now, that exact string actually probably doesn't tell us, maybe may not exist in our taxonomy. But the insight is it's semantically close to a real category. So what we do is we embed the hallucinated string. We do a nearest neighbor search against our pre-embedded taxonomy. And then we map that to our actual category, which is furniture or desk chairs, right? Now, you may be wondering, hey, why does this work, right? So what's going on is the LLM understands what this query is about, and it just doesn't know the specific taxonomy. And the embedding similarity actually handles the mapping. So we are decoupling the understanding the query from knowing the schema. So yeah, I mean, we've seen some interesting results here, but in the matter of time, I'm going to jump to the next slide, which is content. We've spent quite a good time in query, so let's kind of talk about content, right? So this is kind of conceptually very simpler, and I would say, frankly, it's often the best place to start if you're implementing LLM enhanced search, right? Now the idea is, you enrich your catalog with structured attributes that are extracted by an LLM. So look at the before and after here, right? You have a product called Cool Modern Couch with a description, comfortable seating for your living room. This is what you have to work with for retrieval. Now, after LLM enhancement, what you have is the same product now has material, say, leather, and classification, which is living room or sofas, right? Now, when someone searches for gray, leather, modern sofa, let's say, right? You can match on maybe 4 different structured signals that you've got, instead of hoping that, hey, this whole lexical search is picking up the right keywords. So I think the main advantage is this is economic, offline processing, so you run it once per product. It's amortizing your future queries, right? Say, you have a billion product and you have about 10 million queries per day. You're paying the enrichment cost just once, and you're getting the benefit 10 million times, right? So that brings us to the fact that there's an alternative approach to query understanding, which is pretty underappreciated. So you might have heard of this. It's called bag of documents, just like bag of words, right? And this is underappreciated because what we're trying to do, instead of trying to figure out what a query actually means directly, we're learning from what users actually want. Now, the setup is, for a query queue, you basically let there be a set of documents that the users found relevant, which is they clicked on, purchased, whatever signal you have. And we treat these documents as relevant documents as a bag, and that defines the user intent there. And the learning is users, say, who want to search for, I don't know, leather couch, right? Actually want maybe leather family of materials, not just like an exact match leather, right? So this is something the LLM might not know. It's behavioral and it's not semantic. Now, why is this different from, say, embedding the query? I would say the raw query embedding basically captures the linguistic meaning, and the distal, the vector, is capturing the behavioral meaning here. So the limitation, there's definitely a limitation here. That's obvious, right? You need behavioral signals. Now, for tail queries, you don't have the behavioral signals. So this complements LLM-based query understanding rather than kind of replacing it. So that brings us to the next thing, which is what is the similarity, right? So now you have rich signals on both sides, which is your structured query features and you have structured document features, right? How do you combine them? The key idea here is, can we do attribute-wise similarity rather than a single holistic score, right? Because that gives us interpretability, because when something goes wrong, we can identify which attribute match actually failed. So let me show you the formal ranking function here, right? I think in similarity ranking functions, this is actually an English version of the mathematical ranking function, right? So it's a linear combination of feature functions, each with some sort of a learned weight, right? You have BM25 on the name, and then BM25 on description. Then you have like classification match, materials similarity, all of that stuff. And the score is a weighted sum. Now, material similarity is actually not an exact match here. We use, say, embedding cosines here. So the red is kind of similar to maroon and crimson as well, but maybe not blue. So for weight learning, we can use random search, which is, let's kind of try a random weight combination and evaluate NDCG on that validation set, right? You may be wondering, why not do something fancier, right? So, Bayesian optimization or even lambda rank, for example. We tried Bayesian optimization. It gave very similar results with more complexity. And lambda rank, again, it requires features to be differentiable, which some of ours are not. So for 10 parameters, I would say random search is hard to beat in a sense, right? And I think the relationship here is also surprisingly robust, because if you perturb weights by 20%, NDCG actually changes by less than 0.5%. Now, I mean, how do we validate that each signal is actually contributing, right? So that's where you get to ablation testing. So ablation testing is how, this methodology is pretty standard, right? Basically, okay, let's see if this works. Okay, so this methodology is pretty standard, right? Which is, let's kind of hold all other weights fixed and vary from 0 to some maximum, and then we measure the NDCG, right? Now, the key thing is, how are we going to re-optimize any of the remaining weights after we remove a feature? So, say for statistical significance, yeah. So for statistical significance, we actually use a bootstrap resampling, where basically the concept is a feature is significant if removing it is going to drop your NDCG by, say, more than a confidence interval, right? So that said, let me actually give you the cumulative picture. So this chart here that you see, it tracks NDCG as we add each technique, which is, say, we have the BM25 baseline, and then adding query classification, you get a 4% lift. And then you add something like multi-signal ranking, you get 8% cumulative lift. And then let's say we add bag of documents, right? Then you get 13% cumulative. And finally, adding LLM extracted attributes, you're getting 23% cumulative lift. And then you have, in the end, you have the production hybrid system, where it's slightly lower than our best offline configuration. I'll kind of explain that gap in a moment. But a few observations I would like to make. One is, there's no single technique that dominates. That's one thing, right? So each layer is providing an incremental lift here, and that means signals are actually capturing different parts of relevance, or different aspects of relevance here. And the second thing is, the improvements look like they're just partially additive, right? And the third thing is, the NDCG basically translate. It's a 20% plus lift in NDCG. So coming where I come from, which is ranking products or ranking ads, right? This is actually really good business metric. And the fourth thing is, if you break down by query type, you can see that head queries actually are at 8%, and then tail is at 41%. So the LLM-based techniques actually help where you have traditional signals which are weakest. And I know I have 5 more minutes left, so I'm going to skip to discussing LLM as a judge. So let's kind of do that. Okay, so let's talk about the evaluation, because iteration speed basically often bottlenecks search improvement, right? We all know that human relevance labeling is expensive. It's about maybe 10 to 15 cents per judgment with say contractor rates and tooling. Now, if you want to evaluate that change on, say, 10,000 query document pairs, that's about $1,500 and several days, right? So you can't iterate that quickly. Now, LLM as a judge paradigm is, okay, how can we use LLM to predict human relevance? There are two flavors to this, right? One is a point-wise, which is, hey, given a query and a document, rate of relevance from 0 to 3. And this kind of directly gives you the grade for NDCG. And then there's pairwise, which is, let's say I have a query and 2 documents. Which one is more relevant, right? This is an easy task compared to the other one. And how good is this, right? So GPT-4 point-wise actually agrees with human laborers 73% of the time. We found that. And so for context, human agreement on this particular task is about 82%. So LLM is almost as consistent as a second human. And let me jump to some architectural recommendations, because I noticed that the audience also has engineers from different backgrounds, right? So some actionable recommendations I would say is, firstly, always enrich content with LLMs, because this is low risk and high reward, or highest ROI starting point. You can batch process your catalog, and then you can store them, and you're paying LLM just cost once per document. And second thing is, you can classify queries with LLMs selectively. So don't use LLMs for head queries is one thing we've learned, because you have rich behavioral signal there. Now, the crossover point is when you have, say, maybe less than 50 clicks on a query. That's in a day, right? And the third thing is definitely build generalizable classifiers. This one can be debatable or counterintuitive, because zero shot is typically outperforming few shot, because we've noticed that few shot examples are overfitting to example distribution. And if you must use these examples, I would say use many diverse ones, because not a few representative ones, I would say. And finally, computing offline whenever possible, because you're reserving real-time LLM calls for the true tail, which is queries you've never seen and you can't predict. This can reduce LLM calls by 90%. And yeah, the meta point is LLMs are most valuable where traditional ML fails, right? Which is tail queries, cold start, or cross-domain transfer. They're at least they're least valuable when you have abundant, in-domain supervision examples. And that brings me to the end of my talk. Thank you.
We'll take few questions.
Yeah, hi, I'm Vaishnavi. So my question is regarding the hallucination query kind of a thing that you were saying. Are there any insights into why we would want to believe that this is performing better than in non-hallucination query?
Yeah, I think, as I said, this is definitely counterintuitive, right? So in this case, we have enough data to kind of make a valid point that hallucination is helping. I think I can probably reference a couple of articles there on that. But yeah, we have found it through a very interesting working in production. Yeah.
No, I was just curious, are there any hypotheses regarding?
No, yet to be found. Yeah.
Okay, thanks.
I think we are all familiar with the most popular LLM-powered search platform, Perplexity, right?
Yes.
So I'm curious to know about, is there any commonality between their pipeline and your pipeline? And second thing, if you differ means how come? And if you claim, is it your pipeline is better than that?
Yeah, I'm not privy to Perplexity's pipeline, but I do think there's yet to be a standard. You've definitely seen RAG standards kind of emerge, right? Frameworks, but I'm yet to see this being mature. Yeah.
That's what I want to say. They are following a standard protocol, so that they are in the top. Even they are competing and beating the Google and the all the way.
Yes.
So my curiosity is, are you anyway similar or?
Yeah, I mean, it's debatable that Perplexity is beating Google, but let's go with that assumption. But I would say, the kind of business that we are in terms of say, let's take Amazon for example, right? You're ranking products, and Meta, you're kind of ranking ads, versus Perplexity, where you're doing search for, say, articles. I'm yet to see, if there's any correlation there. Yeah.
Hi, I'm Monica Jain. I'm from GE Aerospace. Hi.
Hey.
Yeah. So my question is regarding LLM as a judge. So when LLM evaluates, does it only understands the text? It bases on the text similarity, or does it also understand the semantic content of it?
Right. So it started with just the similarity, as you mentioned,
Yes.
right? Now we are getting into the semantics, and also, as I mentioned, behavioral aspect is another thing. Yeah.
Yes, but now currently whenever we evaluate based on the prompts and some metrics, it generally hallucinates, and it seems like it is basing on the textual similarity. That's it. So
Yeah. I mean, I think if you take two models, say, baseline models,
Yeah.
without fine tuning them, then yes, you're right. I think
okay.
you're not actually understanding the intent behind whatever the user is searching for. Yeah.
Okay. Yeah. Thank you.
Last question, Mr. Tosh. Last question.
Hi, good afternoon. I'm Satvik, and my question was regarding how right now in search ranking or ordering and relevance, we are using text and semantics behind text. So, do you think using instead of just LLMs, also using vision language models or multimodal alignments in search ranking could help maybe increase the NDCG even more? So what is your take on that kind
Yeah,
of?
I would say, multimodal is, that'll be my next talk, right? So it's as obvious as that. Yeah.
Thank you.
Hello, sir. One last question. So you mentioned about the NDCG gains that were improved after the LLM extracted attributes, right? So I just want to understand how these attributes interact with the rest of the stack.
Sorry, interact with the?
Rest of the stack and the retrieval pipelines.
Right. So, okay. So let's say, these are additive in nature. So which means there are some operations that are happening sequentially, right? And usually there's also some sort of a post-processing that you're doing. And you have to add some, which is why, you also have LLM as a judge, right, in the end. And so that kind of makes sure that you have enough guardrails before you hallucinate and give something to the user. Yeah.
Okay. Thank you.
Sure.
Thank you, Mr. Tosh. Just a token of appreciation from Professor Shishi and the Casimir organization. Thank you.